Great. I'm deeply honored to be here, and as a naturalized British citizen, it's very touching to have those kind words from Her Majesty the Queen. Thanks for inviting me. It's a real honor giving the Queen's lecture today. I'm going to take you on a very fast tour of the field of machine learning and artificial intelligence. And it might seem overwhelming at some points because I'll cover many, many topics, but I hope everyone here gets something out of this lecture. And we're going to start with some of the bigger questions, like what is intelligence? What is learning? Can we build computers and robots that learn? Will they ever be as intelligent or more intelligent than humans? These questions have fascinated researchers for many decades, since the very earliest days of computing. As many of you know, Alan Turing, a brilliant mathematician and pioneer of computing who worked in Cambridge and Manchester, provided what is still a widely used definition of intelligence. We'll get to that in a minute. But of course, Turing is probably best known for his to the public for his wartime work at Bletchley Park, where he helped decode the German Enigma and Lorentz machines, a major contribution to shortening the Second World War. Turing also laid down the mathematical foundations of computing. He defined computing in terms of simple operations that a so-called universal computer can do. Here's an artist's depiction of such a universal computer. It's a simple machine. It doesn't have to look like that with the sort of gears and so on, but it's a simple machine that can read and write ones and zeros on a tape of paper. Here's a universal computer made out of Lego, in case you prefer that. And here are a whole bunch of other universal computers. In fact, every laptop, desktop computer, smartphone, mainframe, lots of these smart devices in our homes are equivalent mathematically to Turing's universal computer, which we now call a Turing machine. But of course, the reason we're talking about Alan Turing is that he had an answer to our first question. Okay, let's be clear. He didn't claim to know what intelligence is, but he developed a test by which we could perhaps figure out if a computer had become intelligent. And the idea behind this now famous Turing test is as follows. You let a computer and a human answer some questions asked by a human judge who doesn't know which is the computer and which is the human. After asking a number of questions, if the judge has to guess which one is the human and which one is the computer, if the judge gets it wrong or can't tell the difference between a human and a computer, then we say that the computer has passed the Turing test. It has successfully fooled humans into thinking it's a human. It's a little bit like this cartoon from The New Yorker, which says, on the internet, nobody knows you're a dog. So if you can fool people, then you can sort of pass this operational definition. Now, of course, answering questions doesn't capture everything about intelligence. We do all sorts of other things. We interact with our world through our senses. We move. We manipulate objects. We achieve amazing feats of intelligent behavior no robot or computer can do yet. But Turing's test helped launch the field of artificial or machine intelligence by creating a way of evaluating whether something is intelligent or not. It's one way, at least, and we'll come back to this question of intelligence later on in the lecture. Now, if we're going to try to build intelligent computers, what are we up against? What do we know about the brain? Well, let's start with some numbers. The human brain has about 100 billion, that's 100,000 million nerve cells or neurons, each with about 1,000 to 10,000 connections to other neurons. And the wiring for these areas in the brain is extremely complex. For example, here is a diagram of how visual areas might be wired to each other. All of this sounds very complex. But of course, a machine that is intelligent does not have to be built exactly in the same way as human brains are. Clearly, there are many possible designs and materials that can achieve the same function. So let's think a little bit about the function of the human brain. Well, so what is the function of the brain? We can think of the brain as an information processing organ that takes in information from the senses, changes its state by laying down memories, and produces actions to control the body. Now, I've used the word information, but we can be very precise about what we mean by this word. Information is the reduction of uncertainty, and it's measured in bits. 1 bit corresponds to the answer to a single yes or no question, reducing uncertainty from 2 equally possible choices. So, if the brain is an information processing system, how much information does it process and store? How do we even calculate that? How much information is there in the brain about the outside world? Well, we've already mentioned that there are 100 billion neurons, and they have 1,000 to 10,000 connections and so on. But maybe all of that is not all that relevant. So let's think about this very carefully. How much information is there inside the brain about the outside world? Well, there are only 2 ways in which information can get into the brain: from our genes and from our senses. The human genome, or DNA, is a sequence of 3 billion base pairs. Each position in this sequence coming from an alphabet of 4 characters. So that means that at most, our DNA contains 6 billion bits of information. That's a gross overestimate. That's less than 1 gigabyte. Okay? Basically, that's the information you have in a USB stick from, not even a modern USB stick, a USB stick from a bunch of years ago, 1 gigabyte. Now, most of the information doesn't come from our DNA. It actually comes, the lion's share comes from our senses, and primarily humans receive information mostly from vision and audition. But how much information from vision and audition? So again, we're going to do a bit of a cheeky back-of-the-envelope calculation to figure this out. Okay, so what is life? Life is basically like watching a DVD quality movie. Okay? So we can estimate the amount of sensory, visual, and auditory information by thinking about a DVD movie that lasts our whole waking lifetime. Now, a DVD can be compressed roughly into about 400 megabytes per hour. So we're going to do this little calculation. 400 megabytes an hour. Let's say we're awake 16 hours a day, 365 days a year. Let's take a lifespan of 80 years, give or take 20 if you want. And that gives us 200,000 gigabytes, multiplying these numbers, which is 200 terabytes. But actually, think about what I've just described to you. That is, every single bit of visual and auditory information that's arrived on our senses for our whole lifetime. But it's hard to argue that we could actually be storing or remembering all of those bits of information. So I'm sure you can't recall the color of the jumper of the man sitting across the bus from you 7 years ago, or how many raisins there were in your cereal bowl in the morning, or every note of music that you've ever heard in your life, or every letter of every word that you've ever read in your life. So for the sake of argument, we need to think about not all of those bits. Most of it goes in and gets rapidly forgotten, not really absorbed. For the sake of argument, we need to multiply this number by something. And I'm going to say, maybe 100th. 1/100th of the bits that are actually received in raw sensory form are probably actually stored somewhere. And we could, argue about whether it should be 10 times more than that or 10 times less than that. But the arguments don't really matter that much. But let's go with 1/100th, or 1%. So that, if we multiply this number by 1%, that gives us 2 terabytes. So we could store the information content of a human brain in about 2 terabytes, which, with that analogy from before, is the number of bits stored on a hard drive like this, which I can buy for about £100 or 100 euros or less. And so it's not a lot, actually. So if we want to build an intelligent computer, we're not actually currently limited by memory storage. That's not the problem here. And the human brain, as marvelous as it is, isn't storing that much information about the outside world. It can't create information, by the way. There's sort of like the fundamentals of the way information is created. Information can be manipulated, but it can't be, new information. Information can be processed, but new bits can't be created out of thin air. So what are we limited by? Why haven't we achieved human-level intelligence if all we needed is a memory stick and a hard drive? Well, one thing that limits our understanding of intelligence, one thing is that we have limits on our understanding of intelligence and learning. And those limits come in the form of theories. So what we need are theories that help us understand the function of the human brain and that help us develop intelligent learning computers. Now, some of you may wonder, what form do these theories take? What are we going to use for these theories? Well, they might look something like this, expressed in the language of mathematics. And I'm going to explain this a little bit. But why mathematics? Well, mathematics is actually a formal language, a precise language for expressing theoretical concepts. So these equations actually mean something, and I'm going to try to describe them to you, 2 important equations for understanding intelligent behavior. So I'm going to focus on these 2 mathematical ideas at the beginning, and then we'll see where that leads. And these 2 ideas have had a profound impact on our theories of both biological and artificial intelligence. So the first equation is known as Bellman's equation. And it's due to this American engineer, Richard E. Bellman, who you see here. Bellman's equation tells us how both biological organisms and artificial machines could take actions or make decisions so as to maximize long-term rewards. So let me explain that with an example. Bellman's equation is best understood by thinking about a simplification of all decision-making problems. So consider this lab rat, let's say, who has to navigate a maze to get some reward, in this case, the cheese. Now, we think of the location of the rat in the maze as the state of the rat, and the actions the rat can take are moving, say, left, right, forward, and backward. And actions can take you from one state to another, often unpredictably. Now, some states, like the one with the cheese, have rewards, and some states may have bad outcomes. And the goal of the rat is to take a sequence of actions so as to maximize its long-term rewards. So this rat in the maze is the way we're going to think about these things, and we'll come back to what that really means. Now, Bellman's equation makes an important distinction between the immediate reward of a state, like, for example, the fact that there might be cheese at a particular location, and the longer-term value of the state. Okay? These are different. So I'm rewriting Bellman's equation with words here. And what it says is, if we want to know the value of a state, how valuable it is to be in a particular location in the maze, well, yes, the reward that you get in that location matters, but then there's this other long term below, which is basically saying that you should, if you add to that maximizing over all actions, the sum over next states, the probability of the next state you might end up at, and then the value of the next state. And that's a bit complicated, but it boils down to the following. If the rat is in the location where the cheese is, clearly that location has value for the rat. But if the rat is in the location next to the cheese, there's no cheese over there. But if the rat takes the optimal action, which is to move to the cheese, then it gets a reward in the future. So the value of being next to the cheese is much higher than the value of being very far away from the cheese. That's the long-term value. Now, the rat in the maze is a parable for all decision-making. Should you buy that flashy car now, or should you save to buy a house later? Should you mow the lawn on a Sunday afternoon, or should you read the paper and relax? Should you eat a mushroom that you found in the forest? You know, all of these are decision-making problems that we make all the time. And we're constantly trading off, say, immediate rewards and long-term values. Now, the real beauty of Bellman's equation is that if you could enumerate all the states, all the different states, all the different actions that you could take and the rewards for a particular problem, then Bellman's equation gives us the long-term value of each state and also tells us what the optimal sequence of actions and decisions is. Okay? So if we could just map that out for us, it's the equation for how to make all decisions in life. And that holds whether we're talking about a theory of optimal human decision-making or understanding animal behavior, like foraging behavior of bees, finding some nectar, let's say, or if you want to build robots that can make intelligent autonomous decisions. So this equation, we need this to understand decision-making. The second idea I want to describe is Bayes' rule, due to Reverend Thomas Bayes, who you see here. Bayes was an 18th century English nonconformist minister who had a keen interest in mathematics. And sadly, his greatest work was published posthumously and read before the Royal Society in 1764. Now, actually, it turns out that Bayes' rule, which I'm about to talk about, was independently discovered by Laplace earlier. So if you're French, you might want to call it Laplace's rule, but in Britain we call it Bayes' rule. And Bayes' rule has stuck. Okay. The other anecdote is that although this image is used to represent Bayes, a historian looked at this image recently and said, well, that couldn't possibly be Reverend Thomas Bayes because he's not actually dressed the right way for a nonconformist English minister. But we still use this image. So that's not Bayes, and this is not his rule. This is Laplace's rule. But anyway, we move right along. In his seminal paper, he formulated what we now call Bayes' rule, which lays down the basis of modern probability and statistics. And again, I'm going to rewrite this equation. I love equations, but sometimes you have to write them in words. So I'm going to rewrite it in words, like this. So Bayes' rule tells us how to update our beliefs in hypotheses in light of data. So imagine you're a scientist and you collect some experimental data and you have multiple hypotheses that you're considering. Bayes' rule tells us that the probability of a particular hypothesis, let me see if, I don't think you can see a tiny pointer here, like a bee, a fly flying around. Okay, so the first term here is our beliefs about different hypotheses before observing the data. That's called the prior, okay? Bayes' rule tells us that the probability of a particular hypothesis after observing the data is gotten by multiplying the probability of the hypothesis before observing the data, that's called the prior, by this second term here, which is the probability of the data given the hypothesis. And then you have to renormalize that because probabilities sum to 1. So that's the sort of normalization constant in the bottom. And now let me be clear. Here, when I talk about data, I mean anything that's measured, anything that's observed. And when I talk about hypotheses, I mean anything that's uncertain, any kind of knowledge you want to extract from that data that may be uncertain and not directly observed. And when I talk about probabilities, I really mean quantification of beliefs, okay? Not frequencies, okay? And now, like Bellman's equation, the importance of Bayes' rule goes well beyond any single field of science or engineering. So if you think about the problem of visual perception, when you open your eyes and you look out onto the world, how do you know what's out there? Okay? How many people have seen this image or recognize what's in this image? A few of you, I see some hands, yeah. Now, if I tell you there is a dog and a tree, and the dog has his head down, and you can see the body of the dog, can you see what's in the image? I don't know if you can see my pointer, but no, you can't see my pointer either. Trust me, there's a dog in there. I'll leave it up here for a few seconds while I talk about it. So think about the problem of visual perception. When we open our eyes, the things that come onto our retina, that's the data, okay? And what our brain is doing at some level is forming hypotheses about what's out there in the world. It's combining its sort of prior knowledge of what kinds of things are likely to be out there in the world with the data to update the hypotheses. That's sort of a model of understanding visual perception and other forms of perception. And in fact, many researchers now think that the brain solves the problem of visual perception by implementing Bayes' rule in some way. So, if we want to build intelligent systems, we'll also need to use Bayes' rule to endow our systems with the ability to form hypotheses and perceive the world. Bayes' rule is also the basis of our understanding of learning. So when you observe some data, you learn something about potential hypotheses out there. And this process of refining beliefs as you receive data forms the basis of this kind of learning. So the transformation from our prior state of knowledge to the posterior state of knowledge that comes from the data is basically a form of learning. Now, I'm going to spend the rest of the talk really talking about learning. And the field that I work in is this field called machine learning. And this is a very interdisciplinary field focusing on both the mathematical foundations and the practical applications of systems that learn from data. And it really combines ideas from many different disciplines. I've shown a few of them over here, but many disciplines have contributed to this field. Now, how does machine learning work? Let me explain it by contrasting it with traditional computer programming. So in traditional computer programming, we program computers by giving them detailed instructions, what to do in every situation. And what this results in is step-by-step, predictable, and fragile recipes. So an algorithm is simply just a recipe for the computer to follow. In machine learning, in contrast, what we do is we give the computer lots of data, examples of inputs and outputs, examples of behaviors we want the computer to mimic in some way, and an algorithm that basically is good at finding patterns in data. And what results is in a more statistical, but also less predictable, more robust pattern matching behavior. That's the real contrast between traditional computer programming and machine learning. Now, there's really been a paradigm shift. Traditional computer programming has not gone away, but machine learning has really become incredibly exciting. It's a very exciting time to be in this field of machine learning. And part of the reason it's exciting is just because of the huge number of applications. Machine learning underlies modern speech and language technologies, things like dialogue systems, question answering, translation, speech recognition, and so on. Machine learning also is the basis of all computer vision systems, things that recognize objects. Many of you have smartphones that put little boxes around people's faces. If you've ever wondered where do those come from, it's a machine learning algorithm that is detecting faces. That's the output of those algorithms. Here's a pretty amazing recent breakthrough from a few years ago in the problem of image captioning. And what the machine, when given lots of data, managed to do was to map from the pixels in an image to text, a caption describing what's in that image. And this is for images that it had not seen before. So look at the captions on these images. On the first one, the computer says, man in black shirt is playing guitar. That seems quite reasonable, actually, as if it even understood what's in the picture. On the second one, it says, construction worker in orange safety vest is working on road. Two young girls are playing with Legos, toys. Boy is doing backflip on a wakeboard. I mean, that one's not quite accurate because it's a trampoline, but, you know, it is a computer after all. You've got to give it a break. So when the community saw these results a few years ago, you know, maybe 2-3 years ago, we were stunned. I mean, 10 years ago, such results would have been you know, well outside of reach. We wouldn't have thought it was possible. And of course, these are cherry-picked to make the computer look good. On many other images, it does silly things. But the fact that it could get this far was already incredibly exciting. So it's really an exciting time. And it's not just these traditional areas of machine learning and AI, but scientific data analysis is another area where machine learning is being used very heavily to analyze data, suggest hypotheses to test. In the commercial world, machine learning underlies recommender systems and advertising algorithms that we're now so used to interacting with online. I quite like that, actually. That's going to be shopping centers of the future. Something that is certainly in my sphere of interest these days is autonomous vehicles, self-driving cars. So the idea of machine learning for self-driving has actually been around since the mid-1980s, but it's now becoming a reality. So what you see here is a slide, the big white thing in the middle is a slide from Alvin, which was a self-driving truck built at Carnegie Mellon University in the late 1980s, which could, quote, drive 70 miles an hour on a highway with a tiny neural network. And it's interesting because I saw an interview just recently, just to remind myself of this work, of Dean Pomerleau, the inventor of this thing, talking about it. And the interesting thing is that that self-driving system runs on what's now 1/10 the processing power of an Apple Watch. And the fact that it was driving 70 miles an hour on a road would be pretty frightening, actually. I would want to stay well away from that. We are getting much better. We have a lot more compute power, and the systems are certainly very safe these days. Machine learning also underlies robotics. So this is not a humanoid robot. This is nonetheless a very interesting robot. This is a self-healing robot developed by my colleague Jeff Clune and his collaborators, which was on the cover of Nature a couple of years ago. And this robot learns new gaits if you damage it. And it uses machine learning to do that, just like a human might limp and learn a new gait. Machine learning has become very prominent in recent years in computer games. So you're all, I'm sure, familiar with DeepMind's breakthrough using machine learning systems that could learn to play Atari games at superhuman levels. And then they went on to the ancient game of Go, a very difficult game, and most recently AlphaGo Zero, which learns to play through self-play better than any human. Here's another game. How many people know what this is a screenshot of? Raise your hand if you've seen this. Not many people, but this was a breakthrough from, about a year ago. This is Libratus, a poker-playing computer, winning against human experts. So brains are humans, numbers in parentheses are losses, and all the human experts are losing their shirt to the poker-playing computer. And poker is particularly interesting because it's a game of incomplete information. It's a psychological game, and it's a game where to win, the computer has to be able to bluff, in other words, to deceive humans. Machine learning systems are being used in automated trading, in the financial markets, in many, many other areas. I won't go through all of them, but I think you've gotten a flavor of all these different areas already. So why has there been an explosion of applications of machine learning? Why didn't we achieve this 20 or 30 years ago? And there are a few factors that have been really, really important in the last few years. One of them is that we have vastly larger data sets. That's a big difference from the 1980s and 90s. We also have vastly bigger compute resources. Large data centers with many GPUs and CPUs there. And we also have some better algorithms. We have some better ideas for how to train these machine learning systems. But I would mostly credit the large data sets and the big compute power. And some of the algorithms that we have now that are most successful are actually based on some older ideas. So I'm going to talk about one of them, which has been really revolutionary, which is deep learning. Many of the recent breakthroughs in machine learning are based on this area called deep learning, which is in some ways a rebranding of an old idea called neural networks from the 1970s. So let me explain what deep learning is. So what are neural networks? What's deep learning? So neural networks are tunable, nonlinear functions with many parameters. So in this example, what we're seeing is image classification. So on the input, what you see is an image, this image of some scene going into the neural network. And then on the output side, you see some words, dog, cat, boat, bird, etc. And what the neural network here is trying to do is map from the pixels in an image to the word that labels the image. And the function that this neural network computes from inputs to outputs is computed using layers of what are so-called neurons. And I'm putting those in quotes because they don't really correspond anything to human brain neurons, but people like to call them neurons nonetheless. Now, it's called deep learning because the networks have many layers, so they're deep, not because they're based on some deep idea. Okay? And the weights connecting these neurons are tuned to reduce errors on some training data. So you give it lots and lots of examples, and the algorithms get better and better. And this is an example of supervised learning that was alluded to in the introduction. And you can extend this to do other kinds of interesting learning. Now, deep learning has been wildly successful in the last few years. But although it's been successful, it's important to mention that it has some limitations. AI is not going to be solved by just throwing deep learning at problems with big data. Deep learning systems are very data hungry and very compute intensive. So they might take millions of examples to learn something, whereas actually humans are quite good at being economical with the amount of experience that we need to learn. Deep learning systems are very poor at representing uncertainty, and I'll come to this later. They're generally uninterpretable black boxes, lacking in transparency and difficult to trust. Again, this was alluded to in my kind introduction. And they're easily fooled by adversarial examples. So let me explain what an adversarial example is again. And just to be clear, I'm giving an overview of many ideas in the field from many, many different people. I will, don't want you to think about these things as all, my things, and I try to give credit for these. The idea of adversarial examples really stunned people in the field. So here is the basic idea. Here, the neural network or deep learning system correctly classifies the top image as a school bus and the bottom image as a dog. But here's what you can do. You can give a tiny perturbation to that top image, a perturbation that you wouldn't be able to see by eye. You add a tiny bit of variation to the pixels. You get that other image on the other side, which looks to us like a school bus, and the one below, which looks to us like a dog. But the neural network confidently classifies those as ostrich. Okay? And in fact, you could choose any category and find some tiny perturbation and make the neural network confidently misclassify that image as anything that you want. So you're the adversary, and you're messing up what the neural network does. And this is obviously disturbing because we want our systems to be very robust. Now, so how do we move beyond deep learning? What's next? What are other ideas in machine learning that are worth talking about? And one of the ones that I'm really keen on is this area called probabilistic machine learning. So we really don't want systems that are confidently wrong, like I showed you with the adversarial examples. We really need machine learning systems that know when they don't know. And one view is that a probabilistic approach to machine learning helps us both better understand learning and also overcome some of the limitations that I talked about of current systems. And I know I have lots of equations on this slide, but I just need to put this up because the probabilistic approach is actually very simple. It takes two basic rules from probability theory, and it uses those to think about systems that learn from data. And in fact, Bayes' rule, which I presented to you, follows from these two even simpler rules called the sum rule and the product rule. And so the mathematics of learning, prediction, model comparison, and so on follow from these simple rules of probability. And I won't go into details about this, but I just want to mention that this is not in opposition to deep learning, which is very topical and very exciting. In fact, it helps extend deep learning to what's now called Bayesian deep learning. So why would that be interesting? Well, what we want is systems that have low uncertainty where they've seen data. You can see sort of in this system is trying to learn a function, and where it sees the data, those are the black dots, it has low uncertainty about what the function is, but the system has high uncertainty where it hasn't seen data. That's where you see the big cloud of uncertainty coming along. And so this is particularly exciting because this notion of uncertainty in AI systems is really important if we want to be able to trust them and if we want them to make decisions. I want to highlight a couple of other areas that I think are very interesting. And one of them is some work that we've been doing on a system called the Automatic Statistician. And the problem that system is trying to solve is that there's so many opportunities from understanding patterns in data, from building models, making predictions, and making decisions. But there simply aren't enough machine learning scientists, data scientists, and statisticians to get all that value from the data. So what we'd really like is to build systems that help automate some aspects of model discovery from data. Pre-processing data, searching over models, finding a good model, and interestingly, explaining what has been found to the user. So this is a system that's at the core very different. It's the opposite of a black box. The computer, we're using the computer's intelligence in some ways, to try to explain what is done, what is discovered to the user. So the computer is aiming to be interpretable and transparent. In the automatic statistician system that we have, what it does is it takes data, tables of numbers, and it reasons about a bunch of different models that could have fit the data. It finds a good model for the data, and then it writes a report. So in goes data, and out goes a report in English with plots and text and so on. And here are just some examples of the first page of a couple of reports generated by the automatic statistician. These automatically generated reports are 5 to 15 pages long, with text, plots, tables explaining the patterns, and so on, and ending with a section on model checking, which tries to test the assumptions of the model, and so on. And more examples can be found on the website. And the principles that underlie this are these same principles I've talked about. Bayes' rule is being used to search over models, and a form of Bellman's equation is used to allocate resources to decide on how much computation to do. The last area I want to highlight is an area called probabilistic programming. And this is an area that I think, again, might have impacts well beyond AI and machine learning to many fields of science and engineering. The idea in probabilistic programming is that we're going to write down models as computer programs that can simulate data. Essentially, any sort of simulator of a system. You could think of it as a simulator for an economic system, or a climate simulation, or a physical system, or a nuclear power plant, whatever you want, some kind of simulator. Now, you have a simulator. Simulators can generate fake data. You can simulate, imaginary data from a simulator. But what you really want to do is you want to understand real data. Now, what probabilistic programming allows you to do is it takes that simulator and it combines it with something called a universal inference engine that can automatically invert that simulator and figure out what the unknown things were given the observed data. In effect, what probabilistic programming is doing is it's implementing Bayes' rule on computer programs. Okay? In that inversion that happens in Bayes' rule, going from the data to the hypotheses. And I really think these tools could potentially revolutionize the sciences. I mean, they could be used, probabilistic programming languages could be used to express theories, scientific theories as simulations of predicted data, and then those theories could be updated in light of new data. This is hugely exciting for the sciences, but interestingly, we're also using this kind of tool within Uber to help us better understand cities, to help us understand driver supply, rider demand, so that we can optimize things like transportation for everybody. We want to make the whole system more efficient. And just a few weeks ago, we released this open source project to the world, which is our internal probabilistic programming language called Pyro. And this is interesting because, again, I'm trying to bring threads together. This probabilistic programming language brings together deep learning and probabilistic modeling. Okay, so we can express deep learning models, but we can also express all kinds of probabilistic models. And in fact, the probabilistic models we can express are what are called universal probabilistic models. And that's related to Turing's universal languages. Okay, so this was just rushing through some foundations and some ideas at the current state of the art. But what's the future going to hold for us? And what will this future of machine learning give us? Now, we've seen a lot of depictions in science fiction, but what is the reality? And of course, here I can only speculate. I don't know what the future is going to be. But even based on trends we see now, we can make a few guesses about the future. We are likely to have brain-computer interfaces and many advances in adaptive neural prostheses. And this is an area that Professor Klaus Robert Müller is an expert in. These systems will learn to interface with our bodies and brains. Machine learning is also going to help us in the sciences with learning systems that automatically analyze complex data sets, formulate hypotheses, and design and run new experiments. We'll likely have intelligent personal assistants, companions, robotic toys. That looks a bit scary to me. I wouldn't want my daughters playing with that. But you can get the idea, right? You know, they're going to be in our homes in some way. Self-driving cars and AI-assisted driving will increasingly make its way into our daily lives, changing the structure of cities and giving precious time back to people, making transportation safer and more efficient. Over 1 million people die every year in road accidents, and many of those could be prevented if you had better algorithms. Self-driving cars, here's how, just to depict things, here's how an Uber self-driving car sees its world. It has to detect the objects around it, it has to predict where they are and where they're going, and it has to decide what to do every fraction of a second. And so you can see where ideas like deep learning and Bayes' rule and Bellman's equation might come in handy when you're trying to build something like this. So in the future, we're also going to very likely see electric affordable air taxi services. And initially they'll be piloted, but eventually autonomous. And again, this is something, the piloted versions are something that we're trying to launch in a few years. There'll probably continue to be many military applications of machine learning and robotics, such as robotic warriors and drones, but there's a lot of worry about this among the AI community. So there is actually a very strong campaign of AI researchers trying to lobby governments to have a ban on lethal autonomous weapons. And this is something I certainly strongly believe in. But similar technologies can also be used for very peaceful, very important purposes, like rescue missions and hazardous environments. I think medicine is going to be transformed by the convergence of genomics and AI, making diagnosis and treatment much more precise and personalized. We're going to have access to vast knowledge in almost any human language. We already kind of have these tools, but they're just going to keep getting better. We should be able to ask questions in any language and get answers virtually instantaneously back. And we have kind of things in our homes that are moving in that direction. So these are just a few examples of things that are likely to happen in the not too distant future. So let's come back to some of the earlier questions we started with. So will computers ever be as intelligent or more intelligent than humans? So first of all, I actually think this question is flawed. So intelligence is a vague word that stands in for a huge range of properties and abilities that we have. And I think in some ways we're living in a pre-Copernican era of intelligence. So let me explain what I mean by that. Before Copernicus, people thought that the planets and stars revolved around the Earth, that we were somehow at the center of the universe. And then Copernicus came along and shattered this view. So we're just, a planet around the sun, nothing particularly special about it. So similarly, our definitions of intelligence are very centered around human notions. But I don't think we should see ourselves as just, as some sort of pinnacle of intelligence. Maybe we should see ourselves as just one of many kinds of intelligence. And in some ways, computers are already much more intelligent than we are. In some ways. So, nobody would be foolish enough to challenge a calculator at the task of multiplying two large numbers, or challenge Deep Blue at chess, or challenge a sat-nav system at navigating in a new city, or challenge Google search at knowing trivia, right? So, in principle, I don't see any reason computers can't do anything humans can do eventually better. So we should think about the consequence of this in the long term, in the very long term maybe. But at least in the near term, the vast amounts of data that surround us, coupled with the advances in AI and machine learning, provide us with really tremendous opportunities for bringing many benefits to society. All right. Thank you.
So, wonderful talk, Zoubin. I think a lot of people may have questions, and I start with one. So you mentioned, maybe we can sit. You mentioned that there's vast amounts of data, but I can see situations where you don't have data, right? So, there may be situations in driving that occur so rarely that you never have them. Or, if you have some jet turbines, you will never get a data point where the jet turbine blows up. So can you say something, maybe also taking this as a starting point to challenges that are there?
Yeah, I think this is an excellent point, and many of the advances have really happened in places where we can get lots of data. But we really need machine learning and AI systems to work both where we have lots of data and where we have small amounts of data. And actually, many of our big data sets are just large collections of small data sets. Like, for example, we might have a huge amount of medical data, but on each patient we might have a very tiny bit of information, a few medical tests and so on. And that's really going to mean that we need better methods. We need methods that are much more data efficient, methods that are robust to those environments we haven't seen, like the turbine at its extreme, or driving in conditions that you've never encountered before. So building in that robustness to the heavy tail of events that can happen is still a big challenge. And that's why any estimate that you get of when something is going to happen, you have to think, add a few more years to it for when it's going to happen really robustly.
Yes, and in particular, you mentioned the importance of having estimates for the uncertainty, so that ties very well to your answer. So maybe I can ask to the audience. I'm sure that there are lots of questions around. I cannot see anybody, but so there's a question over there. Maybe you can get the mic to there.
You mentioned that you don't see a reason why computers shouldn't be able to do anything that humans can do given a few years' time. Does that mean you expect us to reach some sort of strong AI that also combines all of that?
I think in the way people define strong AI, they tend to define it very much in human-centric terms. I think in principle, there's no reason we shouldn't reach that. I think in practice, most of the interesting applications of AI are not those that mimic humans, because we already have humans. There are a lot of humans out there. The applications that augment humans, that give us what I would like to think of as superpowers, right? Give us the ability to do things that we weren't able to do before. So I would really want to encourage people to think about AI not as a competition to humans or a threat to humans, but as very powerful tools that we want to use to improve our lives and our society and so on. But whether in principle we can get there, I think, unless we think there's something mystical about humans, then there shouldn't be any reason why we shouldn't get there.
So maybe a question on this side. Yes.
Thank you for the interesting talk. Could you put, how do you think about the development of quantum computing and towards artificial intelligence?
That's an excellent question. There's been a great deal of excitement about quantum computing and quantum machine learning in the last few years. I'm certainly not an expert, but I think that the potential hasn't paid off yet, but it's pretty clear that if we build better quantum computers, certain computations will be achievable much more efficiently. And those computations that are amenable to that will greatly benefit. But not all computations will be sped up by quantum computers, is my understanding.
So to add to that, right now we're using GPUs. We need something to play around in 10 years, no? So, very happy. So, Ralph?
Microphone.
Thank you. So one of the appeals of neural networks is that they mimic the brain, the neurons. And I think many people appealed by that. But is there also evidence in neuroscience that the brain performs Bayes' rule as it processes information? Or is this a bigger gap to jump?
That's a great question. And I spent some of my career being a neuroscientist. So I was interested in these questions. There's an active community trying to understand how the brain combines information from different modalities, how it combines prior information with the evidence it gets from its senses, and so on. And Bayesian models are quite good at mimicking behavior, but people haven't figured out how neurons would actually do that. So Bayes' rule is sort of more relevant at the level of cognitive science to understand normative or ideal human behavior in various perceptual tasks, whereas neural networks have sort of been more inspired by the lower neural level. And bringing those together is a big challenge. But there are people working on this. Some of my colleagues in Cambridge, in fact, work on this.
So I'm just wondering, is there anybody, so on the Twitter side, is there any questions? So please get one question from there.
Yeah, we got a question from the UK. What way would you think is best to approach addressing the real social issues that may stem from the spread of robotics and AI technology, so that these technologies continue to innovate while limiting their potentially negative impacts? Long question.
Yeah, this is an excellent question, and this is a question that has actually been occupying my mind quite a bit in the last few years. So, whereas a few years ago I was mostly focusing on the technology and the algorithms and the mathematics and so on, over the last few years, it's become clear that the AI research community needs to engage with some of these societal and public policy questions. And I've been engaged with various organizations, including the Royal Society and the Leverhulme Center for the Future of Intelligence and so on, which are really interdisciplinary and looking at these issues. And governments have also started looking quite almost urgently into societal issues around AI. So in the UK, we have an all-party parliamentary group on AI, and we have a House of Lords select committee that's also looking at AI. And by engaging with these various organizations, it's quite clear that some of the solutions need to come through taking the benefits that we get from AI and making sure that they're distributed in a way that reaches out to all segments of society. So the solutions are not easy. They have to do with changes in policy, which I'm not an expert on, but certainly aspects of education are incredibly important at every level of the system. Diversity issues are also very important to make sure that the AI community reaches out to all segments of society. And so we also need to think about the regulatory environment for corporations in the sense that the use of data can bring lots of benefits, but also comes with some risks to privacy and so on. And so there is, again, just to cite, there is a recent report by the Royal Society and the British Academy on the use of data, which encourages a principle, which is that data should be used to maximize the flourishing of human society. Yeah.
So we have one question from Sebastian, the beginning, and I would like to see some hands in the back. No?
So can't see you. Thanks for the very nice talk. I was wondering, at the beginning you contrasted a little bit the traditional way of procedural programming to machine learning. And I think there are problems where the traditional way of procedural programming recipes works quite well. If we want to prepare a cake, then the recipe might be a good way to do that, rather than observing 1 million cakes in the world. So is there any way to combine these two, or is there any value in doing so through simulation or whatever?
Yeah, there is definitely value in combining these views and these different approaches. One of the advantages of what I call the traditional programming approach is that you can make those systems verifiable. So you can ensure that that algorithm has a certain behavior. You can even prove mathematically that it has that behavior. Machine learning systems are notoriously difficult to verify. They're sort of statistically verifiable, but they might fall over. Also, the kind of procedural way of writing computer programs is a great way of incorporating prior knowledge into machine learning systems. And so probabilistic programming allows you to do that. You can write down a model that is mostly a computer program with a few bits that are machine learned from data and mix and match as you wish. And so there's definitely great promise there, but there hasn't been enough work at that interface.
So one question in the back and one by this young man.
Is there already an AI implementation which passes the Turing test?
There was I think it was a year or so ago, year or two ago, there was an instance of an AI system that managed to fool a human. Mm-hmm. It made the press, but I think people then quickly kind of moved on from there and said, well, that wasn't a big deal because, you know, it's not all that reliable. It wouldn't fool everybody. I think the Turing test was brilliant in, I think, 1952 or 1950 when Alan Turing proposed it. But people now are trying to think about more diverse ways of assessing intelligence. Because again, intelligence is not one thing, it's quite a diverse thing. So there was a workshop about a year ago called Beyond the Turing Test, where people propose many other tests. And really, it should be a moving definition.
Okay, so maybe one last question here. Okay, so two last questions, so, but we have one.
Taylor?
Okay, please.
Thank you for your nice presentation. I have a question, maybe a little bit specific. I want to know that is there any improvement of diagnose some permanent sickness like epilepsy or others that you can mention by AL? If yes, I mean, which approach is better to work in this area? Thanks.
I'm not really an expert, but I think that applications of AI and machine learning in biomedical problems is hugely promising. In fact, my colleague, Professor Mueller, is
So
more of an expert.
If you're at TU Berlin, then there's a number of lectures where you, I mean, for example, Benjamin Blankert's lectures on brain-computer interfacing and so on. So, but next question.
So about the first question, actually, Professor Müller talked about when you in a situation where you don't have much data and it's maybe new or it has low probability. Are there any good models on how to approach such a situation and maybe form new solutions from earlier solutions you already had in more probable situations?
Yeah. So I think there are two aspects to solving that problem. One of them is identifying when you're in a new situation. And most machine learning systems are terrible at that right now. They just don't know that you're throwing something new at them. They will blindly go and do whatever they were doing before. So first, you have to recognize you're in a new situation. And then you have to come up with a solution to that new situation. And now that sounds like it's bordering on creativity. But let me just explain at least one way we might be able to approach that, which is sometimes new solutions are compositions of pieces of other solutions. And we would really like systems that are not limited to fixed architectures or fixed sets of solutions, but that can compose new approaches to solving new problems. Our automatic statistician at a very, very rudimentary level tries to do that. It tries to compose new models based on different building blocks. We call that sort of a language of models, and sort of the words are composed to produce new sentences, you could think.
So thank you very much for your questions, and I thank Zoubin for answering them. Okay. Thank you so much.
Thank you very much.
Yep. So please stay for one moment and Danke. We would like to, can we have some sound please for me? We would like to pass on to you this document. It says, I guess it's in English, right. We would like to thank Professor Zoubin Ghahramani, Professor of Information Engineering at the University of Cambridge for the Queen's Lecture 2017. Artificial Intelligence and Machine Learning from Understanding Computation in the Brain to Building Self-Driving Cars. The Queen's Lecture was endorsed by Her Majesty Queen Elizabeth II on the 27th of May in 1965 in Berlin. This series of lectures is a manifestation of the special relationship between the city-state of Berlin and the United Kingdom of Great Britain and Northern Ireland. Berlin, 21st of November. So thank you very much.
Thank you very much.
This is a small present that should remind you of your visit to Berlin. It's the so-called Berlin Bear with a number of features on it.
Lovely. Thank you.
And before... Nee, ich brauche aber das Geschenk. Before we all leave, I would like to ask the Excellencies, Sir Wood, would you come up once more in the evening? This may be unannounced, but you're prepared for such occasions. We'd like to give you a small present, which is in remembrance of 20 years of Queen's Lecture. We'll transfer to your home if it's too big.
That's extremely kind, thank you. Yeah.
And with this, I would like to invite you up to our Lichthof for a small reception. Thank you very much. Thank you.
That's great.